Welcome to this presentation in the Corona session of this year's NAMIO Annual General Meeting. My name is Johannes Kunze and I'm a system architect within the Corona R&D department, responsible for the architecture of flow meters. In this presentation, I will talk about smart sensors. Well, you might ask, what's actually a smart sensor? A sensor could be smart if it knows everything about the process to be monitored, and in addition everything about itself. Therefore, a smart sensor is really powerful in process diagnostics and self-diagnostics. The latter is a major aspect in functional safety, which I will address later on. Welcome to today's agenda. I will start with a brief introduction and then I'm going to talk about things which could make a sensor smart. Process diagnostics and functional safety. Functional safety, SIL, is according to the standard 61508. It's a pleasure for me to present you the Corona SIL strategy for our future devices. Finally, I will close with a summary. Let's start with the introduction. Let's have a look at process plants in the last decades. A good field device within these plants measures accurately and reliably a specific process parameter. In today's complex plants, more information than just flow rate, pressure, temperature, or level is required to control the process. We need process diagnostics. In case of safety loops, functional safety becomes more important. You need a functional safe field device with self-diagnostics with high diagnostic coverage. That's quite a lot of diagnostics which I just mentioned. Since more diagnostics may result in false alarms, these smart devices could reduce the device availability or even the plant availability. Therefore, the question is, does it mean more diagnostics, less availability? Well, it's a challenge for us measurement instrumentation companies to provide you accurate, reliable measurements with lots of process and self-diagnostics without reducing your plant availability. Now let's continue with the process diagnostics. Let's start with the process diagnostics for flow meters. For a variety of measuring principles, some process diagnostics have been defined in the NE 107. We consider measurement principles from variable area, EMF, Coriolis, ultrasonic, up to turbine measurements. The blue marked areas are desired diagnostics according to the NE 107. It's a kind of wish list. So we have here diagnostics as, for example, the empty pipe detection, a corrosion detection, which is important for electromagnetic flow meters, or for Coriolis flow meters by the analysis of mechanical transfer function of the vibration measuring tube, or the diagnostics of entrained gas. But all these diagnostics are qualitative diagnostics, which basically show if a measurement is affected by these effects. Then we have conductivity, velocity of sound, or viscosity, which are quantitative diagnostics, which describe the process product. And what's available currently on the market? We see it right here. Here, the wish list has become reality for many diagnostics, as you see. There are quite some smart sensors on the market. Well, variable area meters obviously are not smart sensors. But for other measurement principles, we have the empty pipe detection, which is a quite simple diagnostics. We have the entrained gas diagnostics, but this is really complicated because you would like to detect entrained gas. Eventually, you would even like to detect the amount of entrained gas. But often it is not even possible to measure the process product in case of entrained gas. Then there's viscosity measurements for Coriolis meters. And this is quite interesting because you would not expect a Coriolis meter to measure viscosity. The measurement of a Coriolis meter is based on an oscillating flow tube. Measuring viscosity means viscosity changes must affect the tube oscillation. Unfortunately, it is unavoidable that the primary measurement, mass flow, is affected by viscosity changes. So this is a good example for getting a new feature which degrades the main function of the device. A similar wish list in the NE107 is available for level meters. Here we consider measurement principles based on floats, change of the capacitance, pressure, RF or vibration. Anything which affects the measurement should be detected, such as corrosion, spurious reflections or density changes. Furthermore, there are product-related diagnostics, conductivity or permittivity. Let's have a look what's available on the market. As you see, the RF-based sensors seem to be the smartest. One example, a radar-based level device uses a difference frequency for distance measurement. The amplitude of the reflected signal at the surface in the tank could be quite useful for diagnostics. It is the reflectance of the product in the tank. Therefore, you could detect foam or permittivity changes of the product in the tank by just observing this signal. Now I would like to focus on a diagnostic which was quite critical for a long time: entrained gas and flow measurement. In general purpose measurement devices as Coriolis mass flow meters, entrained gas typically stopped the entire measurement. Now we are able to measure with entrained gas and perform diagnostics. But what's the challenge with entrained gas and Coriolis meters? Entrained gas is a kind of two-phase flow, which exists in various flow regimes. For example, mixed bubble flow, when we have evenly distributed gas bubbles, or fully separated wavy flow. Unfortunately, the flow regime varies strongly. It is quite transient, which makes measurement difficult. Two-phase flow occurs in various situations. Sometimes it could be dangerous, as for example with cavitation, but sometimes it's really unavoidable in the startup of a system or sourcing of storage vessels when they become empty, or the empty-full-empty batching, or if you have outgassing of a process liquid. All these cases have one thing in common. You should be able to measure the process fluid. Well, in addition, you should also be able to detect the entrained gas. So let's discuss the first aspect, the measurement. In Coriolis mass flow meters, the flow tube oscillates, which is necessary to use the Coriolis effect. Within this oscillation, the liquid and the gas phase have a relative movement, which causes a damping of the oscillation. In addition, the gas bubbles are compressed, which also damps the oscillation. The resulting oscillation amplitude of the tube varies a lot and becomes quite small. Furthermore, the signal-to-noise ratio decreases by entrained gas. We have quite strong transients in the density and the mass flow, and therefore the flow tube oscillation frequency varies strongly. And finally, the signal-to-noise ratio is decreased. Conventional mass flow meters could not follow the frequency changes, and they could not compensate the amplitude variations. Therefore, the tube vibration could not be maintained. The mass flow meter has quite large measuring errors and finally stops the measurements. This was basically a quite good diagnostics for entrained gas, because typically the mass flow meters stop the measurement in case of entrained gas. These conditions are really challenging, these flow conditions, and we in Corona accepted this challenge. We developed the so-called entrained gas management, a new concept for signal processing. With this type of processing, the meter can measure with any amount of gas from 0 to 100% gas content. And if you have similar measurement conditions, similar pressure, for example, you also get reproducible measurement results. The two key measures in the entrained gas management are direct digital synthesis, short DDS, or the fast frequency tracking. In order to understand these effects of these measures, let's have a brief look at the Coriolis signal processing within a sensor electronics in a Coriolis mass flow meter. So the flow tube is excited by an electromagnetical actuator. The signals for this actuator are generated by the DDS, which is an amplifier and a digital to analog converter. And finally, in the digital world, it's a signal generator. It generates a sinusoidal signal. It's a synthesized sinusoidal signal with a known amplitude, frequency, and phase. And the flow tube oscillates. The oscillation is being measured by two sensors, and the sensor signals are amplified, converted to the digital domain, and demodulated using the signals from the signal generator. There we have really narrow bandwidth demodulation, and therefore the noise generated by the entrained gas can be suppressed. The demodulation generates two complex sensor signals consisting of the real and the imaginary part of both sensor signals. These sensor signals can be used to feed the amplitude control and the phase control. The phase control is the part which is the so-called fast frequency tracking. It can follow the resonance frequency of the tube really fast. And the amplitude control can compensate the amplitude variations of the sensor tube quite well. In our testing, we were not able to stop the tube oscillation, independent of any amount of gas. So the sensor signals can be used, of course, for the most important part, the density calculations, there we use the frequency, and the mass flow calculations, there we use directly the sensor signals. Now we have solved the first challenge. We can measure with any amount of entrained gas. Now we have the second challenge, detect the entrained gas. For this purpose, we make a statistical evaluation of the sensor signals and the drive current and generate the so-called two-phase signal. So what's up with the two-phase signal? Let me give you an example. Here we have a measurement of an full empty batching. Means the tube is empty in the beginning and the end of the batching process. You see the mass flow is in the beginning 0, then it increases up to a certain level, it decreases, and then, we have reverse flow, you see, and at the end, of course, the flow is again 0. Having a look at the density is in the beginning air density, the tube is empty. Then we have water density, a filled tube, and at the end we have again an empty tube, air density. So the smart operator could see that we have obviously entrained gas in the beginning and the end of this batching process. But we are not talking about smart operators, we are talking about smart meters. And therefore we have the two-phase signal. You see that the two-phase signal increases in the beginning of the batching process and in the end of the batching process. This allows us to detect, on the one hand, the entrained gas, and we could even estimate the amount of entrained gas by having a look at the maximum of this two-phase signal. If you are only interested in detecting two-phase signals, we can set a threshold which can be used in the NE107 signaling, which I would like to address in the following. The NE107 specifies the status signal of field devices. Diagnostics should be provided action-oriented and evaluated by using one of the following 4 signals, which you might know: the failure, out of spec, function check, or maintenance required, each with a separate color. Giving an example for the new Optimus 6400 SIL, for Entrained Gas, the meter shows out of spec, shows a message that two-phase flow was detected, and it also shows you a countermeasure check process for Entrained Gas. That's actually what you could see at the screen of the device. Of course, the same status information is provided via bus interfaces. Well, field devices have typically much more diagnostic information, since it's quite hard to understand the problem. In case of a status message, we enhance the status concept in the NE107 by providing groups called sensor, electronics, configuration, and process. A status message is sorted in one of these status groups, so you directly can see if the problem is in the sensor, electronics, or if it's a configuration problem or a process problem. Furthermore, the status groups with variable status signals can be selected by the operator. For example, the two-phase flow. Only the operator can decide if entrained gas is critical, if it is a failure, or if it should not be signaled at all. Our NE107 concept has an additional advantage. Diagnostic information is sorted into process information, you could see it in green here, or into information which is important for the service and maintenance. So self-diagnostic information. This is in blue depicted. So therefore the right information could be given to the respective person. So either the operator of the plant or the service and maintenance people. Well, considering self-diagnostics, we are approaching the second part of this presentation, which is functional safety, which has a lot to do with self-diagnostics. Currently, there are quite some functional safe devices according to the 61508 standard SIL 2 on the market. 5 years ago, SIL devices were quite different than today. SIL devices started with proven and used devices, which were standard devices, which got later on a SIL certificate and the failure rates. Today's devices, however, were developed according to 61508, which is a significant difference. They have higher diagnostic coverage, and therefore they need much more process and device diagnostics, in particular latter ones. All these diagnostics tend to reduce the device availability for the sake of safety. Furthermore, they require a safe prioritization, which is typically quite complicated. Statistics of field devices in plants show that typically 3 to 5% of the measuring points are safety applications. The rest, so 95% or even more, do not need SIL devices. At least they do not want the mentioned disadvantages. Therefore, some field device manufacturers decided to sell 2 different devices, one for SIL and one for non-SIL. This, however, is quite unpleasant. This makes prior use, which is requested in the NE130, quite difficult, because you have really a small amount of SIL devices and it's hardly impossible to make any statistics with this small number. And that's the reason why NAMUR discussed SIL devices in the new version of the NAMO standard device, the NE131. This SIL device should be developed according to 61508, SIL 2 and low demand. It should have, and that's the most important aspect, the same hardware and same software for SIL and non-SIL devices. So it's no differentiation between a SIL or non-SIL device. You buy the same device. Then it's possible to use the prior use approach according to NE130. Then diagnostics should be reduced to the only necessary diagnostics. This does not mean less diagnostics. This means diagnostics, only the important or critical diagnostics should set the failure signal. In particular, if we consider the process diagnostics, only detected imminent irreversible damages which could happen to the meter should be signaled with a failure signal. Other process diagnostics should only be signaled by, for example, out of spec or any other information. Then a SIL device has, of course, to be switched to a SIL mode, and this should be done fairly simple. A lot of parameters which are SIL critical should be set to predefined values, and those which you can configure these shouldn't be many parameters, and they should be documented quite simple. Yeah, and finally, a SIL device should not have a best before date. There shouldn't be a formal limit on useful lifetime in functional safe devices. Besides all these requirements for a SIL device, there are some other things which you could do wrong in the design of a SIL device. I will show you now 3 examples for a SIL device, a present situation on the market and a smarter solution. Let's discuss about the safe parameterization. A safe parameterization should be performed via a safe channel. Well, parameterization was done so far via HART, but HART is not a safe channel because the requirements for field bus communication, such as checksums, for example, or sequence numbers, are not fulfilled. Therefore, SIL devices always on the market need a verification at the local display. So you can still configure via HART, however you have to go to the display and set the device to a SIL mode. This is quite unpleasant if the device is in your plant in 10 meters height, if it's not accessible. Therefore, we thought about a solution which is a little bit smarter. We developed a concept which is certified and patented, which allows you to verify the parameters also via HART. So you can set up your meter completely via HART without accessing your meter. A second example, you all know the 4 to 20 milliamps current output. If the current output exceeds the limits 4 to 20, it reaches the 3.8 or the 20.5 and gets stuck at this value. This is not a critical point. Typically, the devices signal this via an out of spec. However, a SIL device always has a safety function, which is kind of in the way that the device puts out a current which is proportional to the measurement. And, well, okay, if the current is stuck at 3.8 or 20.5, it's not proportional anymore to the measurement. And therefore, you find SIL devices which set a failure signal without even having a problem. It's just due to specification. A smarter solution would be to redefine the safety function that you do not have to set out a failure signal. You set out of spec, put it into the safety manual, and the availability of the device is definitely better. Yeah, third aspect, the entrained gas, which I already mentioned. There we have different situations. Some meters cannot measure with entrained gas. Okay, if they cannot measure, of course they have to set the failure signal. But if you have a meter which measures still with entrained gas, the meter accuracy might be degraded. The meter might not measure that accurate anymore. Therefore, the specified accuracy is not fulfilled. You have to set the failure signal. A better solution would be if you put a safety application condition in your safety manual that the operator should not use the device with entrained gas, or if he uses it, he's responsible for the device in this operating condition. The device signals the entrained gas via out of spec, but it still continues measuring. So this increases your plant availability. All these aspects are part of the Krone SIL strategy, which we realized first time in the Optimus 6400 SIL, the new SIL device in the Krone family. This device has a SIL and non-SIL mode, using the same hardware and software in both safety modes. Well, then proof test for such a device should be simple. You know, SIL devices always have a small number of dangerous undetected failures, which cannot be detected by internal diagnostics. Therefore, you need to make a proof test. A proof test by just pressing a button at your device cannot detect these undetected failures. Otherwise, they wouldn't be undetected by the internal diagnostics. We minimized in the design the number of undetected failures, which maximizes your proof test interval. And if you have to perform a proof test, well, normally you have to do it once every year, it should be possible to make a partial proof test. That's an inline proof test without removing the meter. The proof test coverage for such a partial proof test is more than 70%. Of course, with a full proof test, you have a much higher proof test coverage. Then a safe device, a SIL device, must have a safe parameterization. And this really should not be complicated. It should be as simple as with non-SIL devices. You should be able to make this safe parameterization via HART or a local display, and it should be possible within less than 2 minutes. Yeah, let's talk a little bit more about diagnostics. Many people talk about diagnostics, diagnostic coverage, but actually nobody talks about the timing. Diagnostics are running all the time in the device, but it takes some time until all diagnostics are carried out at least once, the so-called diagnostic test interval. Many SIL devices on the market have a diagnostic test interval of hours, means you get a failure information really late. We want to have quick diagnostics, a diagnostic test interval of a few minutes. Within the Optimus 6400 SIL, you have a diagnostic test interval of 1 minute. So within 1 minute, you get to know if there is a problem in your device. In general, process diagnostics should only be optional, means only diagnostics of imminent irreversible damages result in a failure signal. Well, let's summarize the presentation. I've given you an overview of process diagnostics of smart sensors. In particular, I focused the diagnosis of Entrained Gas and Coriolis mass flow meter. I explained to you how these mass flow meters could measure in case of entrained gas, because in former times this was really difficult. Then I pointed out that the proper design of diagnostics for these SIL devices can significantly improve the availability. These aspects you will not find in datasheets or safety manuals of a SIL device. You can only find it by asking the right questions. So that's what I can recommend when you next time buy a SIL device. And finally, I've explained to you the SIL strategy using the example of the Optimus 6400 SIL, which is a non-SIL and SIL device within one device, has a smart proof test concept and the diagnostic concept, which is designed for high availability of the device. I hope you enjoyed this presentation. Thank you for listening to it.